Alright, so welcome to this tutorial. This tutorial is meant to introduce to you the Fourier transform functions that we've written for you for your ease. Before I begin with the tutorial, there are two or three things that I want to talk about. The first thing is that I am using the desktop version of MATLAB. However, the syntax that I'm going to use is exactly going to be similar to what you're using in MATLAB online, so there's no difference there. There might be a slight bit of a difference in what the layout is, but otherwise the commands or the syntax is exactly the same. The second thing is that instead of writing a live script, I am writing up a regular script, and the reason for that is primarily for the purpose of this tutorial, because this allows me to use a font size of 18, which is much more visible as far as this video is concerned. Live script does not allow me to do that, right? But other than that, the text remains the same, the syntax remains the same. So you should be able to understand the underlying concepts, regardless of whether I'm using a live script or a regular script. Okay. Now, for the tutorial, we're going to be dealing with the breathing phase data that's going to be actually provided to you in the lab tutorial, lab handout as well, on LMS as well. So let me start with just loading into that mat file into my workspace. So this is breathing phase. This is the data I'm going to be working with. This is the mat. So I press tab for auto completion. This is what I'm going to load. An important point here is that I'm working in the current directory, which is displayed over here, and the current directory is exactly where my mat file is, so I don't really need to specify any path here, and that's probably the easiest thing to do. Whatever files that you're going to import, you just place them in your current directory, and the current directory is displayed up over here. Okay, right. Now, breathing phase, as you can see here, so if I press F5 and run this, and so I'm going to get two variables in my workspace, the phase and the sampling frequency. So this is data which is sampled at 93 Hertz, and every second you get 93 values of data, and those data values are actually phase values, as you can read in the handout as well. And these phase values are measured in radians, as we're going to see it in just a bit. So if I were to plot this as a function of physical time, I would have to define a physical variable time. So that is 0. So let me define L as the length of phase, and this is 0 to L minus 1 divided by Fs. So T, remember now, is going to be a vector, which is a time vector, which is of length capital L, and every adjacent sample or adjacent element in this vector is going to be spaced 1 upon Fs seconds apart, and I can just show this to you as well. So this is plot T and phase, and this is the hold on. Yeah, so this is what I get. So this is the phase signal, and this is, remember, this is a signal because this is some physical phenomena as a function of time. On the x-axis, I have physical time here. So this is about 47 seconds of data, and so here, for example, data point that I pick up, so it illustrates that when x, which is the time, is 46.69 seconds, the phase that was measured was minus 8 radians. And remember, as mentioned in the handout as well, this is actual recordings. These are actual recordings made by our senior year students, one of which is your TA as well. Okay, so this is just an illustration of what the phase looks like. Now what we want to do is we want to analyze this in the frequency domain. To analyze this in the frequency domain, we will take the Fourier transform. And the Fourier transform, we're going to use the function that we provided for you, we've written for you, and that is of this form: x, capital X, comma f equals frft, and small x, which is actually phase. So I want to have the Fourier transform, take the Fourier transform, or perform a Fourier analysis of the signal phase, and then I provide the sampling frequency as well. Okay, and if I press F5, So by the end of when the script executes, what I have in my workspace is capital X, which are the Fourier coefficients, or the Fourier domain, the Fourier domain complex representation, as you would see in the handout as well. Okay, and just to illustrate, and then there's the Fourier transform is actually specified in tandem with two variables. So there's a capital X, which represents what the Fourier representation is, and f is the frequencies at which the Fourier representation is evaluated at. So this is a very, very long vector. So you can see 2,177 elements inside the vector. Let me just pick up the first 5 to illustrate what I mean by this description of the Fourier transform in tandem with these two vectors. So if I just pick up and let me take the transpose of this, so because right, so this is the first 5 elements of the vector capital X, and F1 5. Right, these are the first 5 elements of the vector F. Now, how are these two related? How is the capital X vector and small f vector related? They may seem independent to you, but they are actually not. So what this represents is that the Fourier representation at 0 Hertz, or the Fourier coefficient at 0 Hertz, is this complex number, right? Fourier coefficient at 0.0214 Hertz is this complex number, which is the second element of X, capital X. For the third element in F, which is 0.0427 Hertz, 0.0427 Hertz way, the Fourier representation is this, and so on and so forth. The fourth is this, the fifth is this, where the fifth frequency is 0.0855 seconds. So that's why both of them need to be, you need both of them to be able to specify what the Fourier representation is. Now, what is it really? So as you read in the handout, the complex number may seem complex, but that's a very, very nice complex representation. The absolute value of the complex number represents the magnitude of the sinusoid of a particular frequency, and the phase represents the phase of the sinusoid of a particular frequency. So in other words, if I just take absolute of transpose, let me see. So what this means is that at 0 frequency, at 0 Hertz, which remember is just a constant, right? The amplitude of the sinusoid of 0 Hertz is 0.5838, and the units of forces are radians. The amplitude of the sinusoid at the frequency of 0.0214 Hertz is 0.1491 radians, and so on and so forth. At 0.0427 Hertz की जो sinusoid है उसका amplitude ये है, and so on and so forth. Okay, and similarly, if I take the angle of transpose of x, I would get a similar interpretation. Okay, I can try to visualize what this Fourier representation tells me, right? So, and the way I can do so, I need a phase plot separately, and the angle plot separately, and the magnitude plot separately. I'll just plot the magnitude. So let me plot f with absolute x to try to illustrate to you what this is. So this is what you're going to observe, right? And so there's low frequency elements, and then the high frequency elements are almost null, or they're not really there. So it doesn't really make sense for me to be able to see what this is. So let me just zoom in here. So if I press zoom, yeah, and just zoom in from 0 to, let's zoom in from 0 to 5 Hertz. Okay, so this is the data that you see. Okay, and right, and so basically the data point, what this means is that the at x equals 0.2564, right, which is your actually the frequency, right? So the frequency of 2.2564 hertz, the amplitude of the sinusoid at that particular frequency is 0.292, and so on and so forth. And you can do this for each and every one. So that's the interpretation of what this Fourier transform represents. And of course, you can go back and say, let me see x recovered, and time equals inverse fresh Fourier transform, and then you have x, and you have f, and you have fs. And let's just see what xr is. So plot txr, and you'll see that xr has the same shape as x. So the inverse Fourier and forward Fourier are really the functions that we provided you, are really the inverses of each other. Okay, so that's the basic underlying interpretation about this Fourier transform and how to use them. Okay.